Good morning. Hello, everybody. And thank you so much for coming to listen to this. If you're listening and watching this, thank you so much. And I'm sure it's not as well. It's a little bit indulgent. It's definitely helping me, but I don't know. And it's something that I can do that is helping me, and I don't have to put it doesn't take too much time, but it's really fun. But also, of course, I definitely will get back to writing the book. So if you're here for the book, and yeah, I can understand wanting to have a nice thing to read. I like that too. So, but this is just helping me so much right now. And, after I get done with my talk, then I'm going to get right back into Strongly Compact Cardinals. And so if you're looking forward to that, it's coming. So thank you so much for letting me just talk here. And so this is completely indulgent. And it's really helpful though to me when I do this, because then if I listen to myself, I'm like, oh, actually, it makes me think about it. So I really want to work on this project. Okay. So this project, I will go ahead and put the first slide up. This project, it could be more of a philosophy paper, or kind of both. And the idea is that we're thinking about the nature of primes. Why are primes so special and so great, and why do humans like them so much? And I think that it's the two qualities are that they're unique and creative. So they're unique because their only factors, or their only divisors, are themselves and one. So they're unique. They're not like a multiple of 2 or multiple of 3 or something. So I guess every number is unique, but these are sort of extra special unique. And also they're creative. They build the other numbers. So every number has a prime factorization, and we can see in our world when we're building. Okay, so they're unique and creative. And so this paper might be about about separating that idea. Can we have a prime sort of lose its creativity, but still be its unique self, and what happens in that world? So, and not oh, I'm going to solve Goldbach's conjecture or something, right? So we can talk about that at the end, but this paper is just about the nature of primes being unique and being creative, and what happens if we shut down the creativity part? What if it can't build? What happens? And what I think happens, okay, so what happens if the prime no longer has its creative abilities? We try to separate these ideas in this paper. Can we separate these ideas? And the conclusion, we can prevent a prime from being creative, and the other numbers, it's still unique, and the other numbers will fill in. I think of it, the image I keep getting in my head is if you get a cut and all the blood, the cells or whatever run to that spot. That's kind of how I feel it is with the primes. If you take one's creative ability away, they're all oh, okay, this is what we're doing now. Okay. So we'll do 2 slides. So the interesting result is that we can kill the creative power of a prime and still have a cohesive structure with infinitely many creative and unique primes. And the bigger picture is that, and the philosophy is the primes work together to build the naturals, and if any prime loses its creative ability, the other numbers will naturally fill in to build the set of naturals. One important thing about what do M and V have in common is that they definitely have they both have all the natural numbers. You could say in M there's multiple representations of 6 and other numbers, so maybe it's not exactly the same, but I would say that they do have all the naturals, and that's a good thing about we're not actually killing the prime, we're just disabling its building ability. So if 2 is not creative, we put it like this, then the other numbers will naturally fill in the role and continue building. So 4 becomes prime, and now you can build the building blocks, and we've seen sort of that then from then on everything's basically the same, except that anything with any power of 2 is going to look different and have a 4 base, and anything that has a 2 in the prime factorization, it'll have perhaps less representations in this world, because you can't use the 2 prime blocks, so one of those representations is gone. Okay, so we'll do 3 slides. Okay, so then I was going to go into theorems, examples of theorems about primes, and whether the theorem highlights the unique nature of primes or the creative nature of primes, or both. And I think also a lot of these theorems are I'm trying to think about why are they exciting, why do we like them, why are they, I mean, they probably can help you do a lot of math, and they're really useful. And also, I think a lot of these things are like, oh, the fact that we can say anything about the primes is interesting to us. If there's any kind of like regularity or anything, that's interesting to us because we think of them as like unique and mysterious. Okay. Okay. I would love to hear anyone's thoughts, or like, if I'm wrong, tell me. Okay, so the theorem star, I put Goldilocks conjecture on here, but otherwise they are theorems. And then, does it highlight the uniqueness or the creativity? Okay, so for Mott's little theorem, a to the p is congruent to a mod p, p is prime. Okay, I said this highlights the creativity. It's sort of one of those. It's like, oh, I can't believe you can say anything about primes. I'd say that sort of highlights the creativity. Maybe because it's unique, that seems like a surprising result or something. I'm gonna say it highlights the creativity. Maybe the orderedness to the creativity or something. I think it's sort of talking about the building block nature of the primes. But okay, there could be arguments. Okay, Goldilocks conjecture, E is P plus Q, P and Q are prime. Every even number is the sum of two primes. I think this one is kind of both, because I think the creativity, because not only are the primes building the numbers from multiplication, they're building the numbers from sums as well. That's very creative. And then the uniqueness, I think, is also what makes it this conjecture interesting. P and Q are so unique, and then like an even number can be written with these two unique things. Isn't that amazing? Okay, so that's what I think is going on. Okay, Euclid's theorem, there's infinitely many primes. I think that highlights the uniqueness. Why is this interesting? Oh my gosh, there's infinitely many of these unique things. But the proof itself is sort of like, yeah, because they're the creatives, they're the builders, so we need them. That's sort of like the proof highlights maybe their creativity. A fundamental theorem of arithmetic: every number, a natural number greater than or equal to what can be written uniquely as a product of primes. I'm thinking that really highlights the creativity, that they build the numbers. I mean, there is like uniquely in that, you could definitely argue that it's there's something about their uniqueness that makes this theorem special, but I think it's really highlighting the creativity. The prime number theorem, the number of primes less than or equal to a number x is approximately x over log x. I think this kind of highlights the uniqueness. They're like special things. We're looking for them. How many are there less than this? Oh my gosh, we know a little bit. We can, there's this many. I feel like that highlights the uniqueness. I hope this isn't like just completely like just arbitrary or something, but maybe other people have other opinions. I might be off on this. Bertrand's postulate, for every n greater than 3, there exists a prime between n and 2n minus 2. Again, I think this highlights the uniqueness. Like, oh my gosh, between a natural number and 2 times that natural number, you can find a prime. Wow, I think that this theorem is interesting because it's not like it's highlighting the uniqueness. It's like, because we think of them as unique, this theorem seems awesome. Yeah. Okay, let's do. Is this? This is fourth. Okay. Okay, this is a little bit about the criteria. I started thinking about, why is the theorem interesting? Because of how we think. Is not necessarily hiding the creativity or the uniqueness necessarily, but also, or perhaps another way to think of it is like, we think of the primes as unique, so then this theorem is interesting because of that. We think of the primes as creative, that's why this theorem is interesting or something. Okay, Chen's theorem, every sufficiently large even, this might come in handy, is the sum of 2 primes or a prime and a semi-prime. And there's like 2002, this was really interesting, the even number is greater than e to the 32.7. Okay, I'd say this is a little bit of both, like Goldilocks conjecture. It's like, wow, these unique things you can find these unique things to sum every single even. That's amazing. And also the creativity. They're building from sums. That's amazing. Okay. Euclid's lemma. If P divides A times B, then P divides A or P divides B. I think this highlights the uniqueness. It kind of just goes back to their prime factor, their not having other factors other than one. Friedlander something theorem. I can't read my handwriting. Infinitely many primes of the form a squared plus b to the fourth. That's interesting. It might come in handy. I think that highlights the uniqueness. Oh, that's interesting. These unique primes, and they can be written in this form. Okay, I hope I'm not contradicting myself. Wait, Hardy, Ramanujan. The number of distinct numbers number of distinct primes in the factor of n is approximately log n. I think this highlights the creativity of the primes. Or speaking about the creativity of the building block nature of the primes. This one was really interesting, Euler. Some 1 over p, where p is prime, that diverges. I think that highlights the uniqueness because we think of the primes as so unique and like they're so kind of like, where are they? And there's not that many or somehow that you might think that this sum is convergent. So that's why maybe the theorem is interesting because we know that they're unique. Okay. Vinogradov. Every odd integer is a sum of 3 prime numbers. I think again that's kind of a both. Okay, this is the 5th page. This might take a little while. Wilson's theorem: if n is prime if and only if n minus 1 factorial is congruent to a -1 mod n. I think this is an interesting result because of the way we think of the primes as unique and like hard to catch, and like this is sort of like a it's almost like Fermat's little theorem, but I said I put that as the other one, highlights creativity. Yeah, that one. It's a little. That was the first one I tried, so I don't know. That one, Fermat's little theorem might be like a uniqueness type, maybe not. I don't know. Okay, guys, thanks for indulging me on that. Okay, I'm just gonna talk for a little bit. Okay. If you're still listening, thank you. If you're not, I understand. Meaning of numbers. Okay. So then I was just thinking about meaning of prime decomposition in M versus V, and this might not be. This maybe needs to be worked on, and maybe doesn't feel comfortable because they have a different concept. In V, prime decomposition is like the list of the primes, and of a natural number is the list of the primes along with their powers. So 360 is 2 to the third times 3 to the second times 5. But in M, I think the prime decomposition is really the object itself. It's not a unique prime decomposition because there's multiple ways to build things. Maybe like from outside, we'd say, oh, those are actually the same. But maybe to them, they are actually different. Because it just really looks very different to them. In M, the prime decomposition is indistinguishable from the number object itself. And so in 360, you can have a base of 2, you can have a base of 3, or you can have a base of 5. And so there's 3 different representations, and I think they would think that those are all different prime decompositions, because to them it's just what are the materials you're using for your building. And can you guys imagine these really, 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 really long primes and like building like this? These structures are like, I mean, I don't know how they survive. They're so big. Okay, so that's 6. Okay, 7. Okay, maybe something like M's version of the fundamental theorem of arithmetic. If n is a number object, there are k representations of n, where k is the number of primes in V that are in the prime factorization. Just like I said with the 360, there's 3. M's version of Euclid's theorem. In M, there are infinitely many blocks with height 1, so there's infinitely many of these long blocks that we need, the prime blocks we need. Okay, bigger picture speaking in levels, like, you know, it's interesting, this M is this physical world, and like sort of similar to like the situation we find ourselves in, because we don't actually have the numbers either. I mean, we don't have the numbers. We don't have the number 9, you know, like where is it? But like it's in the Platonic realm, but you know, we have like, oh, show me 9, so I maybe show you 9 blocks. Like that's what, you know, like someone said, show you. So maybe it's kind of like our world. So, you know, maybe some of the challenges that M has, you know, maybe they're kind of like our challenges. Okay. And then so that should be it. That should be it. You should probably just stop listening. So then I wrote some things down last night. No, I was just thinking about Goldbox. You guys, just this completely speculation and stuff like that. Maybe I was thinking, like, there's no way that anyone's gonna believe if you say you start in a world where Goldbox conjecture is not true, and then you're gonna like fill in the hole. No one's gonna believe that, because it's like that. What happened to that even? Like, all of a sudden it has now, you know, 2 new primes. Like, no one's gonna buy that, you know. But like, please, I'm just completely talking. But what if when the primes get very big? I wrote this down last night. Let's say maybe when the primes get very big, maybe there is more than one set of primes. Like, would we be able to tell if there is more than one set of primes? Like, maybe that's just completely dumb. You know, like, maybe they're kind of like sparkling. You know, maybe it's like quantum mechanics or something. You know, Penrose does this really cool thing where it's like, you look, I don't know it all. I saw like some talk where it's like, you look at this like physical thing, and then somehow has to do with quantum mechanics or something. Okay, I'm just yammering. But I just thought, if you sort of, you know, if you were deleting a prime where maybe it was very, very big, bigger than feasible for the ultra-finitists or something, or maybe you didn't know where the holes were in Goldbox conjecture, but they were some, and you sort of like force with all these M's that are just killing all the primes, and then there's all these healing moments, and they're just doing it everywhere so that you have all the options, you know. I think that the only thing it could possibly work is like, I don't know, is like, you know, the set of primes isn't really fixed or something when you get really, really big. And like, at least in the M's world, like those really long things, I mean, there's a lot of room for mistakes. Like, no, okay guys, thanks for letting me indulge in that. But okay, so I'm gonna keep thinking. I don't know what I'm gonna think about next, but I will let you know if I think of anything cool. Thanks so much for listening, and I hope you have a fantastic Friday and a really great weekend, and lots of math in your life.